All right, how's it going, everyone? Back again for another recitation. We got recitation 7 going right now. And this will be a conservation of momentum problem on this front side. Then on the back side, we'll have another conservation of energy. It's more of like a quick little exam review. If you're watching this on Monday, as you guys know, you have an exam on Wednesday. So anyway, let's get into it. This should be a pretty quick one, not too bad. First question, so we have a jet of air with cross-sectional area A and velocity v hits a wedge in such a way that the volume fraction of the jet that goes up the wedge is F and that goes down the wedge is 1 minus F. And the jet is exposed to atmosphere everywhere, and you may assume that V is low enough that the air density does not change. It's incompressible. So this is really light. I tried to adjust the contrast when I printed this out, but I'll kind of try and trace this. So you've got this jet coming in. We've got, some fraction that goes up like that, and another fraction that goes down like that. And so F goes up that way, 1 minus F goes down that way. Cool. And so first off, right, let's get our control volume going. I'll just draw it like this. Just encompassing all of this, all of that junk. So we got our normal vectors there. Right, and these velocities are shooting out like that, right? So we're going to have some, cosine component, right? So if we take this, that's theta right there, and then the other one there. Right, cool. So now let's go assumptions. It gives us, it's incompressible. Ooh, let's say incomp, right, incompressible. It's uniform. Right, there's no velocity gradients or velocity profiles or anything. It's just coming in, going straight out. Steady. Nothing's changing over time. It's inviscid. And that's just an assumption we usually make with any sort of airflow like this, right? Air viscosity is really low, so we usually call it inviscid. And we can also say, I guess the only other thing is like P equals PATM everywhere. That's because we call this a free jet, right? There's nothing like holding this in place, right? I drew those lines just so you could see like the area of it. But this is just, it's like if you had an air compressor, right? And you just like blow the air compressor straight out in a jet. There's nothing holding that there, right? The pressure is P atmosphere everywhere. It's touching the air everywhere. It's a free jet. So with that, right, we see these four. We can automatically say, hey, let's use Bernoulli's. Or at least that we can use Bernoulli's, because we don't even know what we're finding yet. So it says, for part A, we want to find the jet velocity and jet cross-sectional area at station 2 and station 3, shown in the figure, in terms of V, A, and F. And be sure to show and it's spinner work. You can watch the work, I don't know. In part B, find the force of the air jet on the wedge in terms of known quantities, theta, V, A, and F, and density rho. Be sure to show your control volume, say your assumptions. Well, yeah, just did that and show your work. Cool. All right, so for part A, okay, part A, we want to find some velocity and area, but we don't know anything about these areas over here, right? We don't know anything about the velocities, but we know we can use Bernoulli's. So let's just do that. Let's just use Bernoulli's. Oh, see if you can see that? Yeah, that's fine. Cool. All right, so part A right here, let's do some Bernoulli's. Right, from Bernoulli's, we know along some streamline P plus 1/2 rho V squared plus rho GZ has to be some constant, right? And I guess we can also say delta GZ equals 0, right? It's air. You don't care about gravitational potential energy when you're dealing with air. You don't care about that. So let's go. Since all of these lie on the same streamline, right? We can use Bernoulli's all around, right? There's no discontinuity anywhere. All of this stuff lies all on the same streamline. So we can do all the stuff all over. So I'm just going to say, and the stuff without a subscript, right? I'll say P plus 1/2 rho V squared plus rho GZ. Everything without a subscript is the like free stream stuff. So this is also equal to P2 is also equal to P3. Right, and so we already said all of those can go away. And we also know, right, after we did that, okay, if you go and say all the pressures are all the same, which they are, we already said that, subtract the pressures away, all the pressure goes away. And so we're left with 1/2 rho v squared equals 1/2 rho v2 squared equals 1/2 rho v3 squared. And if it's incompressible, right, boom, all the velocities equal the same. Just via Bernoulli's. Boom. Easy enough. Cool. And so yeah, we got that. It's all velocities are all the same. And now second, okay, so we have coming in here, right? We have some density times some, or we have some velocity times some area, right? That's some Q going in. Some volume flow rate going in there. Right? And it says that we have some volume fraction of the jet that goes up and goes down. All right? It's a volume fraction, and we have a volume flow rate coming in. You can just apply that fraction F to these and get the respective flow rates, right? So we have FQ going up, and we have 1 minus F times Q going down. Right? It's easy enough. So we can literally just use our conservation momentum, and you don't need, I'm not even going to write out the whole equation because it's really not that big of a deal. So if we know Q equals Q2 plus Q3, right? So we know Q equals Q is Q equals VA, right? And so Q2 is FQ plus Q3 is 1 minus FQ. So we have VA equals F V2 A2 plus 1 minus F V3 A3. But all these velocities are all the same, right? All these velocities are totally all the same. So we can just go factor all those out, right? So we have A equals F A2 plus 1 minus F A3, right? And if you go and do all that stuff, right? I mean, we have A2 equals FA, and A3 equals 1 minus F times A. Cool. Pretty basic. All right, but for part B, so for part B, we want to find the force of the air jet on the wedge in terms of all that stuff. This is just going to be concentration of momentum, okay? So we have constant momentum. All right, and I will do the full thing in case you're watching this like out of context. So we have sum of external forces. It's equal to the time derivative term, which will go away. Right, so time derivative term goes away. As far as external forces go, let's do x direction first. So we only have one force in the x direction, right? Just this fx here. So we have fx is equal to the time derivative term run away. Now the control volume term, right? All right, so coming in, we have a negative rho. And since this is uniform and all that, we can just say negative rho. These two v's become the same thing, right? Negative rho v squared. And then this ds term just becomes the area. It's an area integral. All right, so that's coming in. Now, let's go plus the outlets, right? And so outlet 2 up here, we have rho v2 squared cosine theta, right? Because we have this v dot n becomes v cosine theta. So it's v squared cosine theta after multiplied out. And then the area is just times FA. And similar thing for the bottom. We have rho v3 squared cosine theta 1 minus f times A. Cool. And so now just do some basic algebra. Remember v2 equals v3 equals v. So we have f of x. You can go do all the simplifying if you want. It doesn't really matter. You end up getting fx equals negative rho v squared a. Should be 1 minus cosine theta. Honestly, like, as long as you rewrite these in terms of v, this would be a perfectly acceptable answer. I mean, that's fine. You don't need to go and simplify it all crazy, but that's okay. Whatever. All right, now let's go z direction, y direction. It's all the same. So again, we have the only force, right? Oh, and we're ignoring any atmospheric pressure, right? Because all the pressure is all the same everywhere, so we can just cancel that out. And same thing for the z direction, right? So we have fz. Oh, and yeah, if you want our sign convention, right? It doesn't really matter, but whatever. Cool. And then so fz, same thing, except for the inlet, there's no z component there, right? It's just coming straight in from the side. So let's go 2, right? So we have rho v2 squared sine theta, right? That's the vertical component of it, sine theta f times a. And now, right, this one down here for v3, sure, when you dot the normal vector, that's positive, but the actual velocity component is in the negative z direction, right? So we have a negative rho v3 squared sine theta 1 minus f times a. So again, go and simplify it. You end up getting fz is equal to rho v squared a sine theta 2f minus 1. But again, as long as you get these in terms of v, it's fine. You don't need to do any extra simplifying. And then you can also say, right, after you find these, you can say the actual force on this wedge is equal and opposite, right, if you really wanted to. But we care about the magnitude of it, all the same. But anyway, so there's that one, pretty basic. Bernoulli's plus momentum. I just kind of Bernoulli's plus a little bit of strict conservation of mass and then conservation of momentum. Anyway, let's get into this one. Number 2 is the energy equation one. And so we have air at T1 and P1 enters this compressor with the mass flow rate equal to that through a circular inlet pipe having an inner diameter of 1 centimeter. The compressor operates at steady state. Okay, that's important. The mechanical power is input to the compressor at a rate of 3.5 kilowatts. Air exits the compressor at T2, P2. And the diameter of the exit pipe is large, and therefore the velocity of the air leaving the compressor is small, and its kinetic energy is negligible. However, the kinetic energy of the air entering the compressor is not negligible. The compressor is not adiabatic. Assume air obeys the ideal gas law with R equals that, and justify any, okay, whatever. All right, so first off, A, you want to determine the velocity of the air entering the compressor and determine the rate of heat transfer to the compressor. So let's get our control volume going, and this is going to be really tiny, but you know what I'm talking about. It's okay. So, whatever. Cool, and then, yeah, we've got that work coming in, whatever. Who cares? All right, so assumptions. There's going to be a couple of big ones here. Assumptions, so it's steady, it gives us that. It is compressible, right? We're given all sorts of pressures and temperatures. Ooh, compressible. Geesh. Compressible. See, we can also say, since we're dealing with air, right, delta GZ is 0 again. We don't care about gravitational potential energy. And this is a big one. KE out equals 0, okay? But that said, V out does not necessarily equal 0, right? But kinetic energy, if you recall, I guess this is specific kinetic energy. This is that 1/2 v squared term, okay? That equals 0. And we're saying that's the case here because if we have such a huge area out here that the velocity is really small, you know, like 0.05 meters per second, when you plug that velocity itself in, that's not like a trivially small velocity, right? You're still gonna have some volume flow rate. But when you divide it in half and then square it, that becomes super, super tiny, right? Or just square it and divide it by half. But so that becomes super, super tiny. It's called, you know, higher order terms disappearing, right? You can ignore the higher order terms for small answers. So that's what that means. Steady, compressible, say uniform, and inviscid. That's pretty much all we need. Should be fine. I don't think we really need anything else. Cool. So for part A, this is just a thermo thing, right? Just, you know, m dot equals rho VA. And so we know we're trying to find velocity. So V equals m dot over rho A. We need to find density, right? Remember P equals rho RT. Okay? From, you know, it says ideal gas law, so we can use that. So we can say rho 1 is equal to P1 over R T1. And plug in all that stuff. And remember, you have to use all of the absolute values, right? This is an absolute, so you have to use Kelvin, you have to use absolute pressure, all that stuff. So P1 is 100. And then I put that into pascals, so we have to multiply this by 1,000 because it gives that in kilojoules. So 287. And then times, see, 20 plus 273, 293. So we get rho 1 is equal to like 1.18 or something. Yeah, 1.1892 kilograms per cubic meter. All right, so from that, we can get V. We're given m dot is 0.025, just gives it to us. And then over 1.1892. And then the area is, what's the area of the pipe? It's 1 centimeter, so it's what? Pi 0.01 squared over 4. I'm getting V. V is a really big number. You know, relatively big number. 267.6 meters per second. And this is also a good sanity check for oh yeah, so 2 of these things are good sanity checks. One, you know, we did something right, because that's pretty good density for air, 1.18. It's pretty nice. And then it's also a sanity check why we can't say it's incompressible, because that's really fast air velocity. And at that air velocity, for sure, we have to worry about compressibility effects, right? Whenever you get above like Mach 0.3, you end up having to worry about compressibility effects. And speed of sound is about 340 at this temperature right here. So 267 divided by 340, that's much better than like 0.3. It's like 0.78 or something. So that's good. Just another little thing. All right, now part B, this is where the actual energy equation comes in. So thermoform of energy equation. And I'll write the whole thing out, I guess. So we have Q dot, which is what we're trying to find, right? Minus W dot is equal to d by dt CV rho, hold on. I always forget this form. Yeah, I always forget. That one is not in that one. Then V dot N ds. Ugh, such a beast of an equation. All right, cool. But anyway, we make all sorts of simplifications here, so it really doesn't matter. So this whole unsteady term goes away anyway, so that's nice. It's a steady problem, so that's cool. And then again, we don't care about the GZ, so that goes away. So we're left with here Q dot minus W dot is equal to just this control surface term, CS. Right, now let's actually start worrying about sign convention. All right, so for heat flow rate Q that we're going to be finding, negative value indicates heat leaving, positive is heat going in. The opposite is true for work done, right? So compressor work is being put in, so that 3,500 watts, that's negative. So it'll be Q dot minus negative 3,500 is equal to, now let's look at the inlets and outlets, right? So we've got the inlet coming in, so we've got rho 1, and then we've got the stuff on the inside, U hat plus P1 over rho 1 plus 1/2 V1 squared V1 A1, right? And that'll be negative because that's an inlet, right? Now plus coming out, same thing, rho 2, and that should be 1, 2. 2 plus P2 over rho plus 1/2 V2 squared V2 A2. But remember, we set up here, right? The kinetic energy leaving, we can call that 0, so that goes away. So that's nice. And now we can also rewrite this because we don't know internal, this is specific to internal energy, okay? And we don't really have an easy way to go about getting that, but we can use that U hat plus P over rho is equal to H hat, specific enthalpy, is equal to CPT. And I guess we can also say CP equals constant. It didn't say that, like on an exam or like a homework, we'd definitely give that to you. CP equals constant is equal to like 1005 joules per kilogram Kelvin, I think is the unit. 1005 is usually, it's like the number we usually use. It's not a big deal. This isn't thermo class, right? It's fluids. Who cares? So anyway, we can plug that straight in. And then I'm also going to do a little more simplifying. So we can say Q dot plus 3,500 is equal to, I'm going to move the rho VAs out front, so negative rho 1 V1 A1 times what's on the inside here. Well, that just becomes CP T1 plus 1/2 V1 squared, which we already know V1. I should put V1 right there. And then on this other side here too, right, we have rho 2 V2 A2. And then the only thing in here is CP T2. Cool. And well, now you say, well, damn, I don't know anything about V2. I know it's small, but we don't know V2. And I really don't know anything about A2 because it tells us just, oh, it's really big. But remember, rho VA equals m dot. And in this case, it's constant. Or / same for both. Right, we only have one inlet and one outlet. What's coming in has to be going out. So we can slap that on there. So we can have Q dot plus 3,500 is equal to negative m dot CPT1 plus 1/2 V1 squared plus m dot CPT2. All right, and I guess I'll go and plug in the numbers. Might as well. Cool, so it's gonna be negative 0.025, and you can factor however you want, I don't really care. 1005 times T1 is, what was that, 293 plus 1/2, 267. Right, plus, again, 0.025 1005. And this, what, is 50, so what, 323? Cool. Go solve for Q. Everything else, you literally know everything else about it. Solve for Q dot. Okay, Q dot is equal to negative 3640 joules per second. It's equal to negative 3.64 kilowatts. Boom. Just like that. Not too bad. And remember, this is heat leaving. Cool. Opposite sign convention for work and heat flow. So anyway, that's those two. If you need any help or anything, put in the comments or shoot me an email if you have my email. And that's about it. All right. Have a good one, guys.